Salam and welcome everybody. Today's lesson is about the stereoisomerism. In the previous class, we learned a lot of things about the structural isomers, and now it's time to study the stereoisomerism. So the first thing that you have to put in your mind, what is the definition of stereoisomerism? So the first thing you should put in your mind, it is a compound with the same molecular formula and structural formula, which means that the bonds are connected or bonded to each other with no change. But they have only difference in here, which is the arrangement in their space. So how can we deal with such type of isomerism, and what are the types in here? According to the types that we're going to look for, the first one is geometrical isomerism, and it has two names, which is cis and trans. So what is the meaning of cis and trans? The first thing that you have to put in your mind for cis and trans, we are dealing with a double bond. So once you have a double bond or carbon-carbon double bond, you have a probability to have a geometrical isomer. So let's start with what is the meaning of geometrical isomer. What are the conditions of geometrical isomers? So let's take an example in here. Okay. So the first question that hits your mind, why do we have stereoisomerism? What is this stereoisomerism? It says that once you have a double bond or any compound that contains double bond, then the free rotation around this bond is forbidden. You can't make any rotation. So the hydrogen in here will be up and this one will be down. It's not the same as this compound when you have a single bond and you have hydrogen around. There is a free rotation around the CC carbon, and that's why these atoms can rotate as well. So like there is a free rotation in here, but there is no free rotation around the double bond, and that's why you will have different compound. So this is the first thing. Why do we have stereoisomerisms that are called cis and trans in the double bond? Because the rotation around the carbon double bond is not allowed. Okay, so what do we have in this case? Once you have a carbon double bond, this is the first condition. This is the first condition, you have a double bond. And the second condition says that you have a double bond, right? But if you have different atoms that are bonded to each carbon, you must have different, these must be different so that you have a stereoisomerism. And the same thing here, these must be different. I mean, each carbon must bonded to different atoms. Give us an example, let's go and see. Let's take this one. Suppose that you have carbon-carbon, you have hydrogen, and here you have CH3. So these groups are not the same. These are different. Okay. On the other hand, you put hydrogen in here and CH3 in here. Okay. So look at hydrogens in here. You just notice that these hydrogens are opposite to each other. So once you have the two atoms that are opposite to each other, in this case, we can conclude that we have a geometrical isomer and it's called the trans. Okay, so if I ask you to name this compound, you notice that you have a double bond in here, and then you have hydrogen and hydrogen. These are opposite to each other, or you can look at these CH3s because these are identical atoms and opposite to each other. You can say this is a trans. So I can say this is a trans, all right? How to name this alkene? We take the longest chain. We have 1, 2, 3, 4, and actually this is but 2-ene. Okay, so this is a trans. You must draw it in trans. But if you have a trans, then you have cis, which is the other geometrical isomer. Okay, so this geometrical isomer could be like C and C. You have a double bond. Okay. You have hydrogen, hydrogen, and CH3, and you look at this, you notice that the hydrogens are in the same phase and the methyl groups are in the same area, like together. So we can call them cis, okay? And we just write the rest of the name of your alkane. So you can start counting the alkenes from 1, 2, 3, 4. Then it's bute 2-ene. Okay, so this is the geometrical isomer. Okay, the first thing, the atoms in each carbon must be different. So if I ask you a question, let's say CH2 double bond CH3. My question is there any geometrical isomer in here? Do we have geometrical? First of all, you look at this carbon, which is in the double bond. Okay, so you have a probability to have that. You have hydrogen here and CH3 here. You have hydrogen and you have hydrogen. So what you see in this case, you have carbon and this is bonded to two hydrogens, two identical groups, and then you don't have any geometrical isomer in this case at all. So we're done with that. But what happens if we have a carbon double bond that is bonded to hydrogen, bromine, and you have CH3, CH2, let's draw here, CH2, CH3. How can I deal with such an example? First of all, you notice that there is no identical groups. All of these are different. So I can't determine which of these will be cis and trans. But we have a solution for every issue. First of all, you will divide this compound to two sections, and then you will start arranging these atoms according to their proton number. So you look at hydrogen. Hydrogen has a proton number of 1, and bromine has a proton number of something that is higher. Okay, so in this case, bromine will take number 1 because it contains a proton number greater than hydrogen, and for hydrogen it will take number 2. And the same thing in here. You notice that this carbon is bonded to carbon and carbon, so we still have the same thing. But this carbon is bonded to another carbon, and here we have no carbon. Then it will take number 1, and this is number 2. You just notice that you have number 2 that are on the same level, and you have 1 that is in the same level. So in this case, we can say this is cis, and you can call it as you like. Question is, where do we get alkenes from? Where do we got them? Actually, alkenes can be produced by cracking, and you could produce them by elimination or the dehydration of alcohol. So we have different reactions that lead to produce these alkenes. So let's take a simple alkene that looks like CH3, and we have CH, we have hydrogen here, and we have a bromine, and we have CH2, and we have CH2, and CH3, and CH3. So if we add sodium hydroxide that is dissolved in ethanol, then what will be the product in this case? According to what we learned in previous classes, once you have alkali, which is a strong base, in the presence of ethanol, then we will have reaction of elimination of HBr, because we have a bromine in here. So according to what we have, I just want to draw this in the display formula in here. We have hydrogen that is bonded to 3 hydrogens. I have carbon that is bonded to 3 hydrogens. So according to what we have, we're going to eliminate the HBr. So we can remove this in here, okay, or you can take the Br from here. So if you take it from this area in here, you will have a double bond, and you could have another compound with a double bond in here. Okay, so the possible products that you will get, so we'll draw it like this. you will have CH2 double bond CH, CH2, CH2, CH3, okay, and the probability of having a double bond which is between, it will be like CH3, CH double bond CH, CH2, CH3. So according to what we have, you could have three products. In this case, the three products indicates that you will have this one, which is the first one, and you have this. How can I make two compounds of this? First of all, you have to remember the geometrical isomers. The geometrical isomers indicate the presence of cis and trans. So it will be like this, CH3, okay, you will draw CH, and here you have hydrogen, this is double bond, this is C, and you have hydrogen, and here you have C2H5. Then you could draw it in this form when hydrogens are on the same level, and this is cis, or you can draw it like this, like C, you have hydrogen here, double bond, CH3, and C, and here you have hydrogen here, and here you have C2H5. So just notice that here the hydrogens are in the opposite to each other, and this is trans. So you have three possible products in this case. If I want to draw that in terms of a skeletal formula, you can say like you have methyl, how many carbons we have? We have 5 carbons. Then you can draw this like this. It's cis, it will be like this. And yeah, so this indicates the methyl, and this is CH2, and this is CH3, and these are the hydrogens. So this is in case if you want to draw that. And what about this? How can I draw it? It looks like this. You have to draw like this. Yeah.